Okay, in section 3.3 we're going to look at some properties of logarithms, and we're going to start out talking about product rule. If I have the log of a product, then I can split that and write it as a sum of the log of each of the factors. So the log base b of the product of m and n is equal to the log base b of m plus the log base b of n. Okay? So the log of a product can be rewritten as the sum of the two logs. So for example, the log of 10x, I can split that up as the log of 10 plus the log of x, and now evaluating the log of 10, log base 10 of 10 is actually 1. So the log of 10x is really 1 plus log of x. And this is what we call expanding a logarithm. We're taking it from a single log and writing it out into multiple logs or multiple terms. The quotient rule, if I have the log of a quotient, remember a quotient is like a fraction, a division problem. So the log of a quotient is the difference. Okay, I'm going to subtract the two logs. So it's the log of m minus the log of n. So if I have the log of x divided by 2, I can rewrite that as the log of x minus the log of 2. And again, this is what we call expanding the logarithm, taking it from a single log and writing it either as multiple logs or as multiple terms. Okay. Power rule. The power rule is when we're taking the log of some power where the bases don't match. The base of the log and the base of the power don't match. Remember, that's one of our basic properties. Okay? In that case, we can take the power, the exponent moves out front as a coefficient. So the log of m to the p power is the same thing as taking p times the log of m. So in the example, natural log of x squared, the squared would move out as a coefficient, so it becomes 2 times the natural log of x. And again, this is still considered expanding the logarithm, even though it still only has one term. Okay, we're kind of simplifying what we have going on. So if we look at these examples, okay, number 1, we want to expand the log of 100x. Well, 100x is a product. It's 100 times x. So we'd write that as the log of 100 plus the log of x. But this log is base 10, and log base 10 of 100 would actually be 2. So this simplifies to 2 plus log of x. Okay. In example number 2, we have a quotient. So if it is a quotient will turn into a difference. So it's the natural log of e cubed minus the natural log of 7. Well, our other properties still hold true, so this natural log of e cubed is actually just 3. So it becomes 3 minus the natural log of 7. Number 3, natural log of square root of x. You might say, well, we don't have anything that deals with square roots, and you're absolutely correct. Remember, we take roots and we rewrite them as exponents. The square root of x is the same thing as x to the 1/2. And now it's a power. So the power rule says that becomes 1/2 times the natural log of x. Okay. So an example of product rule, quotient rule, and power rule. Okay. Number 4, I want to expand this problem, a little bit more complicated, a few more terms going on. So if we look at it to start out, the first thing you notice is that it's a quotient. So we'd have log base 6 of cube root of x minus log base 6 of 36y to the 4th. Well, our cube root, we would want to write that as an exponent, so that's x to the 1/3 minus, now this is a product, so I have log base 6 of 36 plus log base 6 of y to the 4th. Okay. So my first term is a power rule. The log base 6 of x to the 1/3 is 1/3 times the log base 6 of x. So that's simplified as far as we can go. Okay. Minus, and I've got to keep parentheses here because I'm subtracting this whole thing, log base 6 of 36. Well, 36 is the same thing as 6 to the 2nd power, so log base 6 of 36 is really 2. Plus, I've got a power rule down here on the end. I have y to the 4th power, so that becomes 4 times log base 6 of y. Okay. So now I've got all of my properties taken care of. I just need to now distribute the negative. So I have 1/3 log base 6 of x. And I'm going to put the constant at the end. So I'm going to put -4 times log base 6 of y, and then -2. And all I did there was 2 is a constant, so we put the -2 at the end because our constants are generally going to be our last terms. And this is the expanded version of this complex looking log up here. It breaks it down into much simpler pieces. Now if I want to condense, then I'm going to take something that's written as multiple terms and use the properties in reverse to write it back as either a single value or as a single logarithm. So in this example here we have log base 4 of 2 plus log base 4 of 32. Well, 2 and 32, neither of those are powers of 4. But if we see that we have a sum of logs, then we can take that and write it back as a product. So 2 times 32 would give me 64. And 64 is really 4 to the 3rd power. So this whole thing just simplifies down to the value of 3. It condenses down to that one single value, that one single term. When we're doing the condensing, we have to make sure that our coefficients on all of our logarithms have to be 1 before we can condense and apply those properties. So in this example, we have 2 times the natural log of x. Then we need to use the power rule and rewrite that back as the natural log of x squared. And now that each log has a coefficient of 1, since it is a sum of logs, then we can rewrite that back, condense it down into the product, making it the natural log of the product of x squared with x plus 1. So let's see if we can condense these two problems. 1/2 log of x plus 4 log of x minus 1. And you might want to try them on your own and see how well you do before you watch me work through them. Okay? So in the first one, I want to rewrite this as log of x to the 1/2, and this would be plus log of x minus 1 to the 4th. Okay? So the sum means this is actually a product, so it's log of, and x to the 1/2 is really the square root of x times x minus 1 to the 4th. Okay? So kind of doing two things at once here, using our product rule for logarithms. The sum of a log is the same as the log of the products, and then also remembering that x to the 1/2 is really the square root of x. Okay? If we look at example number 2, 3 natural log of x plus 7 minus natural log of x. So the first thing is to take care of this coefficient. So we'd rewrite that as the natural log of x plus 7 to the 3rd minus the natural log of x. And now a difference of two logs condenses back down to a quotient. So it's the natural log of x plus 7 cubed divided by x, and we're taking the natural log of that whole quantity. Okay? So when we expand, we take it from a single log out into multiple pieces, multiple logs, and when we condense, we're generally taking multiple logs and rewriting it as one single log statement. Okay? Now, here's another important formula. Okay, this is the change of base property. So all those problems where we had logarithms that we had to evaluate but we couldn't type into the calculator because it wasn't a base 10 or it wasn't a natural log, this property, this formula right here is what lets us get around that. Okay, it lets us go from a base B to a base of A. So I could really change it to anything, but generally what we're going to be using is either the log base 10, or I like to use the natural log because it works in both situations. As long as these two logs are the same thing, it doesn't matter what your base is. So if we want to use the calculator, we either need to make it as log base 10 or as a natural log, the log of base E. So here we want to evaluate the log base 5 of 140. So using our change of base formula, we could rewrite that as either the log of 140 divided by the log of 5, remember that log means that this is base 10, or we could write it as the natural log of 140 over the natural log of E, remembering that this is really with base e. Okay? Either way works. It doesn't matter which one you use. For whatever reason, I usually just use the natural log, and no particular reason. That's just the one I prefer to use. And once we've got that written as that quotient, as that fraction, okay, now all we have to do is type those things into the calculator. The natural log or regular log of 140 divided by log of 5. And we can get an approximation. Okay, and this one comes out to be approximately 3 7/100. So this change of base formula is what allows us to utilize the calculator for evaluating these logs of bases other than 10 or e. Okay, so same thing here. Try evaluating this one. We've got log base 7 of 2,506. So if we were going to use the change of base formula, and I'm just going to use natural log just because that's the one that I use. It's the natural log of 2,506 divided by the natural log of 7. So if we type that in, natural log 2,506 divided by natural log of 7, we can see that that is approximately 4 200. So hopefully you have that same calculation. And again, once you get to this point, okay, all this here is just simply typing it in the calculator. Okay, so very simple, but you have to remember the correct order. That it's the base, the numerator is going to be the natural log of what I was originally taking the log of, and then the denominator is going to be the log of whatever my original base was. Okay, so once you know that change of base formula, it makes evaluating these other logs much easier to do now. And also, really, if we type it in correctly, would allow us to graph these other logs in the calculators as well. Okay, so tomorrow we'll field any questions, and we will start working on some practice problems dealing with properties of log and change of base. Okay, we'll see you then.